And when we're in two dimensions, you get either rectangular coordinates or polar coordinates. So if we were only thinking about our xy plane, we can define things as being either rectangular coordinates, where I tell you a certain direction in the x direction, a certain amount in the x direction, and then also some amount in the y direction. Like, what's a really nice ratio? Like 1 to square root of 3, maybe? And so what's square root of 3, like here? I don't know. What if we're thinking about this point? So in rectangular coordinates, this would be 1 in the x direction and the square root of 3 in the y direction. Polar coordinates is saying, I can tell you how far away from the origin I am. We call this lowercase r. And I can tell you what the angle is that I have to turn counterclockwise from the positive x-axis. And that's theta. And correct me if I'm wrong here, with my triangles, with my special triangles. But if the x-coordinate is 1 and the y-coordinate was square root of 3, that means r would be 2, and then theta would be, what's 60 degrees in radians? Yeah, pi over 3. And so this is polar coordinates. In two dimensions, you still have to have two numbers to describe where a point is in the plane. But this time, the first number is how far are we away from the origin in a straight line. And then the second number is what angle in radians do I have to turn counterclockwise from the positive x-axis to be facing the direction of my point. Okay, polar coordinates. I found out the other day that Desmos can do a display in rectangular coordinates, and also Desmos can switch to this if you prefer, where you can see what it looks like with polar coordinates. And so you have these concentric circles, and those circles are values of r, right? And so if I have r equals 1, 2, 3, that corresponds to the r equals 1 circle, and the r equals 2 circle, and the r equals 3 circle. So every point along these circles has an r value of 1, 2, or 3. And then you've got the values of theta right here. So like this line that comes out from the origin, this would be theta equals pi thirds. And this line coming from the origin would be theta equals 5 pi over 6. So maybe that visual helps. It's just a different way of looking at two dimensions. One other thing I should say about polar coordinates is that these aren't unique, really. Like if I say I have an r of 3 and a theta of pi thirds, like that's a point right there, okay? That's r of 3, theta of pi thirds. But I could also call the same point r of 3, theta of 7 pi over 3. Does that make sense? Because if I were to rotate 7 pi over 3 from the positive x-axis, I make a full rotation in 2 pi, and then an extra pi over 3 points me in the same direction. And so maybe it's a good idea to try to keep your theta always between 0 and 2 pi, or if you prefer like negative pi and positive pi. But technically there's an infinite number of ways you could represent the same point, because you could always add or subtract 2 pi from the theta and get the same point back. Okay, so cylindrical coordinates then is basically polar coordinates with an extra z coordinate, right? If this is rectangular, and we have x, y, z, then cylindrical coordinates is going to have coordinates r, theta, z, because now we're in 3 dimensions, and we have to know how high are we in the vertical direction. And importantly, remember r in polar coordinates was the distance from the origin, but now r is going to be the distance from the z-axis. So if my z-coordinate changes, it will not affect the lowercase r value. R is not the distance from the origin, it's just the distance from the z-axis. Theta means the same thing. Theta is still the angle you have to rotate counterclockwise in the xy plane from the positive x-axis. And then z is still z. Wait, any questions about cylindrical? Okay. And then this is where we started to get rushed yesterday, is when we were doing these problems. Like, convert the following coordinates from rectangular to cylindrical. And if I want to convert from rectangular to cylindrical, that means I'm going to be given x, y, and z, but I need to be able to calculate r, theta, and z. And again, conveniently, z is just z. R is found with the Pythagorean theorem, right? Because if this is the xy plane, imagine we're looking down the z-axis, and I've got this point, it's got some x coordinate and some y coordinate. I can draw a right triangle, and then this hypotenuse, the distance from the z-axis, would be r. And so that's just the Pythagorean theorem. And then theta is going to be the arctangent of y over x. Because again, this is the angle theta. And tangent of theta would be opposite side over adjacent side. So it would be y over x. And somebody tell me, what's the important thing you have to remember about arctangent? What about the quadrants? Yeah.
It's not on the right side.
Yeah, the right side is good. Arctangent works really well for the right side. But the problem with the left side of the plane is arctangent will never tell you an angle on the left side of the plane. So if your point is actually in the left side of the plane, then you have to add pi. If it's in quadrant 2, you have to add pi to your arctangent. If it's in quadrant 3, you have to add pi to your arctangent. If your point is in quadrant 1, you don't have to add anything. And if your point is in quadrant 4, you don't have to add anything. But if you end up on the left side of the plane, then you have to do the little add pi thing here in order to make that arctangent work. So it's always good to draw a picture of what you're doing. And so that way you know if you need to add pi or not. In this particular example, I've got -3 for my x coordinate, and then positive 3 square root 3 for my y coordinate. So my point is over here in quadrant 2. And so to find r, we take the square root of negative 3 squared plus 3 square root 3 squared plus 2, nope, not plus 2 squared, right? It's just x squared plus y squared. And then this is 6. For theta, we're wondering about the arctangent of 3 square root 3 divided by negative 3. And this time we will have to write plus pi because we're in quadrant 2. And so that means we will need to add pi at the end of arctangent in order to get the right angle theta. And since this triangle, we talked about this triangle yesterday, has this side length of 3, this side length of 3 square root 3, and this hypotenuse is 6, this is similar to a special right triangle, right? 1/2 root 3 over 2, 1. This is a special right triangle from our unit circle. And that means this angle would be 60 degrees, because this is a 30, 60, 90 triangle. And that means this angle, theta, would be 120 degrees. And 120 degrees is also known as what in radians? 2 pi over 3. So if you put this in your calculator, if you've got your TI-30X2S calculator, and you type in arctangent of 3 square root 3 divided by negative 3, or maybe you just type in negative square root of 3 plus pi, it's going to give you a decimal. It's not going to give you the exact answer, but it should be the same as 2 pi over 3. And then the z is the same. So in the end, my cylindrical coordinates will be 6, 2 pi over 3, and 2. Does that make sense? Okay. If I want to convert from cylindrical to rectangular, that means I'm going to be given r theta z, and I need to be able to calculate x, y, and z. And again, z is the same between cylindrical and rectangular. X is going to be given from drawing a picture and looking at the trig functions. Like if I have this point, and this is r, and this is y, and this is x, and we've got a right angle here, and this is theta, then cosine of theta would be what? X over r. And what would sine of theta be? Y over r, yeah. Because cosine is adjacent side over hypotenuse, and sine is opposite over hypotenuse. And so that means x is going to have the conversion formula r cosine theta, and y has the conversion formula r sine of theta. In answering this type of problem where you're given r equals 4, theta is pi over 4, and z is negative 7, is super easy. Because like cosine of pi over 4 is square root 2 over 2. And sine of pi over 4 is square root 2 over 2. And z is negative 7. So there's your rectangular coordinates. Okay. And here's something we didn't get to last time. It says, convert the following equation from rectangular to cylindrical variables. And so this is not just a coordinate triplet anymore, but it's an equation. And whenever I see a problem like this, what I do immediately is I always write down all of the formulas that I know for converting back between the two. Like r is equal to square root of x squared plus y squared. I could also write r squared equals x squared plus y squared. Tangent of theta is y divided by x. Z is the same between the coordinates. And I also know the conversions the other way, that x is equal to r cosine of theta, and y is equal to r sine of theta, and z is z. And I like to write down everything I have, just so that I kind of have my whole toolbox in front of me. And then when I start thinking about the problem, I just look and see which tools from the toolbox seem to line up. And if I want to convert this equation from rectangular to cylindrical variables, it's pretty easy. My goal is to eliminate every mention of the variables x and y and replace them with r's and thetas. Z is okay, because z is still a cylindrical variable. But I need to get rid of the x and the y. What's the easiest way I can get rid of the x squared plus y squared? Yeah, I could just replace it with r squared. And we're done. That's the answer. Now that equation is strictly in terms of cylindrical variables. Okay. Convert the following equation from cylindrical to rectangular variables. So this time, my equation has a cylindrical variable theta, and I want to rewrite this equation so that it only contains variables x, y, and z. And again, and a smart way to start out might be to say, I'm just going to start writing down all of the conversion formulas that I know. And just see if something starts to click. So the only one that contains a cosine theta is this. So I'd probably try this first, since my equation has cosine theta. And cosine theta then is the same thing as x divided by r equals 1/2. But I'm not done yet, right? Because I'm trying to eliminate all of the cylindrical variables, and r is a cylindrical variable. It's not a rectangular variable. And so now if I want to get rid of the r, I could do something like replace the r with square root of x squared plus y squared. Because I also see this has an r in it. You can change the r into x's and y's. And technically you're done at this point. Now I have an equation that's only in terms of x and y's and z's, right? Z would be allowed, but I don't have any z's. So technically you're done, but I would go ahead and simplify this. Again, this is one of those things we always talk about. If this were an open-ended question, like it shows up here on a test, I would give you full credit for writing this. That would be fine. But if this was a multiple choice question, I would make the correct answer choice like a fully simplified correct answer choice. And what I mean by that is we could multiply both sides by 2 and multiply both sides by square root of x squared plus y squared. And then I could square both sides. And then I could, I don't know, subtract x squared from both sides. And that looks nicer, in my own opinion. In fact, we don't even have to stop there. We could, even further, take the square root of both sides, and we would get like square root of 3x equals y. But I also need like a little plus or minus sign now, because when I take the square root of both sides of an equation, that's a hint that you need to add in a plus or minus. Or you could say something like y equals plus or minus square root of 3x. That's probably the best way to write this. And when I look at this, I can tell that this is going to be 2 planes, right? This equation represents 2 planes. One of the planes is a strictly vertical plane because we don't have any mention of z, right? So z is free to be whatever it wants. And this plane is defined by y equals positive square root of 3 times x. And then there's a second plane that's described by y equals negative square root of 3 times x. And so whenever we have this, cosine of theta equals 1/2, that's the same thing. That's also representing 2 planes. I wonder if GeoGebra can do cylindrical coordinates. Let's try it out. So just because I don't know how to do it doesn't mean it's not possible. But I'm not immediately seeing anything for cylindrical coordinates. And I thought if I typed in theta, it would just give me the variable theta, but nope. Okay. Or maybe it's this, is it the keyboard? There's got to be a theta on this keyboard. So yeah, this is another huge missed opportunity by GeoGebra to make their product useful and user-friendly. But whatever. It means the same thing, right? Just because this is in... Oh, you know what? We don't even have to really rely on GeoGebra for this one because it's kind of two-dimensional. We didn't have any z's anywhere. So I could also say in Desmos, cosine theta equals 1/2. And, oh, I thought Desmos could do this. Polar equations must be linear in R. This is linear in R. How about this? How about theta equals arc cosine of 1/2? Can that work? You can't graph theta as a function of anything yet. Okay, thank you. Whatever. I've tried. Aside from rectangular coordinates, we can use spherical coordinates. And so spherical coordinates is the tricky one. Here's my XYZ space. And the deal with spherical coordinates is we are going to be given a rho, a theta, and a phi. So those are all lowercase Greek letters. Rho, theta, phi. And rho represents the distance from the origin. Like I mentioned yesterday, it's important that you know rho is not the same thing as r, because r is the distance from the z-axis, not the distance from the origin. And theta is the same theta as from cylindrical coordinates. And so theta is still the angle counterclockwise from the positive x-axis. And then phi is new. Phi is the angle from the positive z-axis. And so here's a point in space. The distance from the origin straight to that point is rho. And then this angle from the positive z-axis is phi. And to draw theta here, I would have to draw the projection of this point down onto the xy plane, and then that would be the angle theta. So since we're in 3 dimensions, we still have to have 3 numbers to describe where every point in space is. Now, convert the following coordinates from rectangular to spherical. From rectangular means we are given x, y, z. And if I want to convert to spherical, that means I should be able to calculate rho, theta, and phi. Rho is given by the Pythagorean theorem. So rho is going to be x squared plus y squared plus z squared. Theta is the same theta from cylindrical coordinates, and so we can reuse the same formula. It's going to be the arctangent of y over x. And maybe, if you know you're on the left side of the y-axis, so you're in quadrants 2 or 3, then you might have to add pi. And then phi is the angle away from the positive z-axis. And so if we look at it from the side, where the xy plane is flat to our vision, and this is the z-axis. And here's our point floating out in space. This is the angle phi. And this distance from the origin to the point is rho. And then this distance from the z-axis to the point would be r from cylindrical coordinates. And then this distance from the origin up to that point would be z. So how do I get phi? I could say that sine of phi is r over rho. And that way I could calculate phi as being arc sine of r divided by rho. Or we've got options. We could actually say cosine of phi is what? Z over rho, because it's adjacent over hypotenuse. And so that way phi is the arc cosine of z divided by rho. That's probably easier because that way we don't have to calculate r. And then we could use tangent of phi equals, well, let's just talk about that for a second. What if I wrote down tangent of phi? That would be what? R over z. That would be opposite over hypotenuse. Or sorry, no, opposite over adjacent side. And then phi could be arctangent of r over z. But we don't like arctangent, right? Arctangent has issues. So we just don't like using that in the first place. Arc sine and arc cosine, you don't have to worry about those issues, right? You don't have to worry about like, should we add pi question whenever you're talking about arc sine and arc cosine. And I think in general, we're going to enjoy using this the most. You could use the arc sine formula, but then you'd have to calculate lowercase r. And if you just use phi equals arc cosine of z over rho, then that way you don't actually have to calculate r. And you're all set. So the only thing that could possibly be a little bit tricky here is the arctangent thing, like should I add pi? And in this example, if x is positive 2 and y is negative 10, that puts me down here on my xy plane. So here's the question. This time, should I add pi after I calculate arctangent for theta? No, because I'm on the right half of the xy plane, and so I do not need to add pi. So I don't have to worry about this part. Okay, now let's convert these coordinates from spherical to rectangular. That means these are given to me as rho theta phi. But I need to calculate x, y, z. And what I like to do personally is before I do this, if I'm converting from spherical to rectangular, I just go ahead and calculate r first. And that might be a little bit silly, but I'll explain. Sine of phi is r divided by rho, right? In other words, I could have written r equals rho times sine of phi. Does everybody agree with me there? So r is equal to rho times sine of phi. And now that I have r, x is just r cosine theta, and y is just r sine of theta. We know that back from when we were converting from cylindrical to rectangular coordinates. And then z, let me scroll back up so I can look at my picture and decide how we're going to calculate z. We can start here from this equation and rearrange that to get z equals what? Rho times cosine of phi. So z is equal to rho cosine of phi. Cool. So that's how I would do it. That's how I convert from spherical to rectangular coordinates, is I first calculate r and then I use these formulas. When I was taught calculus 3, our professor just had us memorize that x is equal to rho sine of phi cosine theta, and y is equal to rho sine of phi sine theta and z is equal to rho cosine of phi. And so you can do that too if you want to. But these formulas are basically the same thing. X equals r cosine of theta because r is rho sine of phi. So it's up to you, right? Pick your poison, whatever is easiest for you to memorize or recreate for yourself on a test. I don't care how you do it, as long as you can do it. As long as you can do these problems on a test. I don't really know. I don't really care what formulas you're using. Okay, convert the following coordinates from cylindrical to spherical. And so that means these are given to us in r theta z. And we want to be able to calculate rho theta phi. Rho is once again going to be given by the Pythagorean theorem. And I can draw the picture again. Because here's my point. And then this is rho, this is r, and this is z. So for my right triangle, just use the Pythagorean theorem, and you'll get this formula. Theta is theta. And then I think we talked about this a moment ago, but how do I get phi? I got to scroll up. I can get phi by using this phi equals arc cosine of z divided by rho. Since I have already calculated rho and I know what z is, that will work. Are there any questions so far? No? Okay, stop me, ask questions if you have any. And then I think this is the last coordinate translation we have to do from spherical to cylindrical. And so that means these are given to us as rho theta phi. And cylindrical means r theta z. Z is going to be, and I think at this point we've already kind of figured out some of these formulas. Like if I'm trying to get z from spherical coordinates, that's just going to be rho times cosine of phi from right here. Theta is in spherical coordinates, so theta equals theta. And then to get r, I once again think about what it looks like to have a z-axis and an xy plane and some point out in space here. And this is r, this is z, this is rho. And we're trying to figure out, how do I get r? And I guess I would use the Pythagorean theorem and say r is equal to the square root of what? No, because rho is the hypotenuse. And since rho is the hypotenuse, we would have rho squared minus z squared. That's the way we can get r. I think maybe we even found out other ways of finding r too. like, oh, r is also equal to rho sine of phi. So if you like that better, r is equal to rho sine of phi, we can do that. I guess there's multiple ways of doing the same thing. That's probably the better one to memorize, because that's important for more types of translations between coordinate systems. So that's the one I would use. All right. Now we've got more equations. We're no longer doing coordinate triplets. We're doing equations. And this time I want to convert from rectangular to spherical. And my equation has x squared plus y squared minus 3z squared equals 0. I want to get rid of all the x, y's, and z's and replace them with rhos and thetas and phis. So let me just go ahead and write down a few things. Like, I know that rho squared is x squared plus y squared plus z squared. I know that theta is going to be the tangent of theta equals y over x. I know that phi is such that I don't know, r is equal to rho sine of phi, right? I know that z is equal to rho cosine of phi. I'm just kind of grasping at things right now. And I could write some other stuff down, like x is equal to r cosine theta, y is equal to r sine theta. And just keep writing stuff down, right? Because the more tools you have sitting in front of you, the more, something might inspire you to some kind of action. So, does anybody want to tell me what to do first? What should I do first here? What tool from my toolbox should I try? That's okay. I'll show you what to do if this were me. You notice how negative 3z squared is the same thing as positive z squared minus 4z squared? And now do you feel inspired? Okay, so I could combine that into just a nice rho squared. And then I still have some z's, but to get rid of the z's, I might want to use this formula, just because it gives me z explicitly. And I don't have just z, but I have z squared, and so then I might write rho squared cosine squared phi equals 0. And then I could factor out the rho squared and get rho squared times 1 minus 4 cosine squared phi equals 0. And then I start to think to myself, when would this equation even be satisfied, right? This works as an equation two different ways. Number one, if rho is equal to 0, then the left side is 0, the right side is equal to 0, and the equation is solved. On the other hand, this would work if 1 minus 4 cosine squared phi is equal to 0. which means 1 has to be equal to 4 cosine squared phi. And that means 1/4 is equal to cosine squared of phi. And that would mean 1/2 is equal to cosine of phi. And that means phi needs to be equal to pi over 3. Or, what's another value of phi? So that cosine of phi equals 1/2. Because if it's pi over 3, then the adjacent over hypotenuse is 1/2. But then also negative pi over 3, right?
Do you also do plus or minus 1/2 because you took the square root?
Oh, you're right. That's very good. And so that gives me 2 more options for phi, right? Because it could be pi over 3, it could be 2 pi over 3, or it could be negative 2 pi over 3, or it could be pi over 3, it could be negative pi over 3. And those are all valid. Remember what phi means, though, for spherical coordinates? Phi is like the angle from the positive z-axis. So when we point up towards the positive z-axis, phi is 0. And then as phi increases, it starts to go like this until phi is at pi halves. And then you're in the xy plane when phi is equal to pi halves. And then as phi increases up to pi, you're pointing straight down towards the negative z-axis. And it's just kind of convention. I didn't say this before, but it is the convention for spherical coordinates that we always say rho is positive. I mean, in theory, you could say rho is negative and then point in the opposite direction, right? But just conventionally, people like to write the spherical coordinates so that rho is always a positive number. And for phi, we like to keep phi between 0 and pi. And you could imagine like larger value of phi, like you're pointed in this direction of theta, and then you increase phi from 0 up to pi, and then you just keep going, and it could continue to trace out the circle on the back end. But the convention is that we only allow phi to go from 0 to pi, and if you want to access those points on the back side of the sphere, you could just add pi to your theta angle, and then have theta point you in a different direction, instead of using larger values of phi. And so this is what we try to stick to when we use spherical coordinates. And so that means if we were trying to stick to our convention, then I guess we would say this, that really the valid values of phi here are pi over 3 or 2 pi over 3. And so rho equals 0, that's just the origin. And that happens to be included in these two planes. Would you call that a plane? No, you wouldn't call it a plane. That would be a cone. Yeah. There's 2 cones happening here. Because when I say that phi is equal to pi over 3, we're allowing theta to be all real numbers, right? Whatever theta wants to be. And we're allowing rho to be whatever it wants to be, just all real numbers. And so whenever I say phi is equal to pi over 3, that's talking about a cone, and phi is equal to 2 pi over 3, that's also talking about a cone pointed in a different direction. Let me try to draw a picture of that. So here's the z-axis, and here's the xy plane. this is the cone that we get for phi equals pi over 3. I can't draw stuff in 3 dimensions, but imagine that's like sweeping around the whole thing, right? And then 2 pi over 3 would be the cone that points down at roughly the same angle, or the exact same angle, but pointed down. And I guess we can actually see this in GeoGebra if I just type in this. GeoGebra may not be able to handle spherical variables, but it should be able to handle x squared plus y squared minus 3z squared equals 0. So if I'm right, we have one cone pointing up and one cone pointing down. Yesterday we were talking about quadric surfaces. This would be our last quadric surface that we never found, right? The elliptic cone.
Oh.
It's really a circular cone this time, but I could make it more elliptic if you want. I could just do that. Now it's more of an ellipse when you find the trace. Okay. So we got 5 more minutes. We'll just keep doing these and see how many we can get. But hopefully you understand the point of like how to do those homework problems now, is it's just like write down all of the conversion formulas you know, and then just like stare at the page until you get some divine inspiration to move forward. I don't know. So again, we've got 5 minutes left. I'll try to quickly show you this one. We've got rho equals 4 times cosecant phi. And cosecant doesn't show up in any of my conversion formulas. So maybe I'll rewrite this as 1 divided by sine of phi, because cosecant is the reciprocal of sine, and then secant is the reciprocal of cosine. Yeah, learn your reciprocal trig functions, you guys. And so that way I can write something like this instead. I can write 4 equals rho sine of phi cosine theta. And at this point, if we were lost, we start to, daydream about our conversion formulas a minute, and we think, well, r is equal to what? Rho sine of phi. Hey. And then we, start to think again about our conversion formulas, and think, well, x is equal to r cosine theta, right? And so this is just a plane in space where x has to be locked in at 4 and y and z can be whatever they want. And it's funny because it's not 100% clear looking at the original equation that this would be a plane in space. Rho equals 4 cosine phi secant theta. But then once you kind of work with it, rearrange it, now we see that it has to be a plane. Trying to look for a hard one. Let's try this one. Phi equals pi over 4. I'm going from spherical to cylindrical. And so spherical has the rhos and the thetas and the phis, but we need this to look like r theta z. Specifically, I need to get rid of phi and replace it with r and z. And so one thing I might dream up is that z is equal to rho times cosine of phi. And that means phi must be equal to the arc cosine of z divided by rho. So we might write arc cosine of z divided by rho equals pi over 4. And I can get rid of the arc cosine by taking the cosine of both sides. Now cosine of pi over 4 is square root 2 over 2. And am I done yet? I need this in cylindrical variables, so I need it in r, theta, and z. Ooh, so I can't have a rho. Now I've got to get rid of the rho. Well, rho would be the square root of r squared plus z squared. And so I could write 2z is equal to square root 2 rho, or I could just write square root 2 of z, sorry, times z is equal to rho. And then rho is the square root of r squared plus z squared. Square both sides, so I can get rid of that nasty square root. Subtract z squared from both sides, and then I could take the square root again and get this for my cylindrical coordinates. So in cylindrical coordinates, the equation becomes z equals plus or minus r. And that would also be a cone. I'm pretty sure that's a cone. And it's probably easier to tell from the original equation. Yeah, whenever I say phi is equal to pi over 4, that would tell me that it's a cone. But also think about this in terms of cylindrical variables. If your z vertical distance is equal to the distance away from the z-axis, then that would also give us a cone. I've said this before, but you have to have a great imagination, a great visual spatial imagination for this class.